show some of the very impressive large igneous provinces that we now recognize in Russia. Okay. So with respect to large igneous provinces, we are talking about very, very large magmatic events. Let's see. I know some people here can't see. Can I adjust this at all? Can I move this? Good. Okay. So we're talking about three aspects. Very, very large volumes of mainly mafic and to some degree ultramafic magmatism. We're talking about typically a very short duration of emplacement, and we're talking about events that are mainly intraplate setting. In terms of scale, for some of these events, they are at least 100,000. Oh no. Okay, the pointer doesn't seem to work so well. Okay, it's hard to see. Okay, so 100,000 cubic kilometers, which in terms of the scale of Russia would represent an event that would cover the entirety of Russia to 5 meters. There are events, oceanic plateau events, a type of large igneous province, that cumulatively could be 80 million cubic kilometers, which would cover the entirety of Russia to 4.5 kilometers. We are talking about events that are placed in a very short duration. Some of them are less than 1 million years for such volumes and interplate settings. So they are not associated directly then with plate tectonic boundary processes, not spreading ridges, not subductions, but interplate, and we think of them mainly linked to mantle plumes. Here's a beautiful example of some of the flood basalts of the Siberian trap event when we talk about continental flood basalt type of lips. Those are what I think in the Russian literature is usually talked about as traps. And here is a beautiful example. Another aspect of this is the plumbing system. When you erode the volcanic portion away, you're left with the feeder system. And the feeder system consists of huge swarms of diabase dikes and sills and layered intrusions. This is from northern Canada. It represents our very large, giant radiating dike swarm. Can't really see the pointer there, but on the left diagram you see a swarm that extends out about 2,000 kilometers, radiates away from a mantle plume center on the far northwestern portion of Canada. You see in the image there dikes that are about 100 meters wide going across the countryside. Individual dikes like this could extend down, for individual dikes here, we think could extend all the way out for 2,000 kilometers. And a point about these dike swarms is that we think the magma is generated in the mantle plume center area and injected laterally out through the swarm, sideways in the crust for these distances, so that the magma out here originates from a mantle source area underneath the mantle plume center here and moves sideways through the crust. It's a dramatic idea, but we have lots of evidence for that. I won't have time to discuss that today, though. So, in terms of the lip family, large igneous province family, we consider the flood basalt component, as in this one from the Columbia River, or the preceding image from the Siberian trap event, and the associated volcanic rifted margins, because these are associated with rifting and formation of new oceans. The plumbing system component, consisting of dike swarms, sill provinces, and layered intrusions such as the bush belt. A class of associated intrusive types, carbonatites and some kimberlites are associated with large igneous provinces. and also some silicic provinces, both intrusive and extrusive. In the Archean, there are examples that we think represent large igneous provinces in the Archean. Typically, those are ones which contain komatiated magmas, evidence for high temperature magmas. Much of this is typically continental. In the oceanic areas, we have ocean basin flood basalts, oceanic plateaus that represent mantle plumes coming up, producing large igneous provinces in an oceanic setting. This shows the distribution of large igneous provinces for the last 500 million years. A similar record continues all the way back to 2,500 million years ago. This shows the areal extent of the volcanics and also the intrusive component. Here's the Siberian Trap event. Here's Anton Java, a major oceanic plateau, that together with Manihiki Plateau and Hikarangi, cumulatively in volume, represent nearly 80 million cubic kilometers of material placed in a very short time. This represents a number of other events, and I won't go through all the details there, but you can see that these events cover large areas and therefore represent, as we will see, significant sources of volumes of magma, but also fluids and heat that contribute to ore deposit formation. Okay. The record is very robust. We figure that these things come out somewhere on the planet every 20 or 30 million years. This global barcode, you can see, well populated with red lines marking events back through time. You see a particularly dense abundance in the youngest record, where the oceanic plateaus are well preserved. However, given closure of ocean or disappearance of ocean basins prior to 200 million or so, that prior oceanic lip record is gone. It is preserved in deformed orogenic belts and will probably eventually be recognized and sorted out. But at this point, we suspect that the density of overall lips that we see here, which is something like 1 every 20 million years or so, is actually the true density back through time if you consider the observed continental flood basalts and the predicted number of associated oceanic plateaus. The links are important, and we'll go through some of those. Links with extinction events, very robust. Links with regional double uplift of a scale of about 2,000 kilometers across and a kilometer or so up in association with an underlying mantle plume. Linked with rifting and breakup, we think that every major breakup margin through time, continental breakup margin, is associated with the large igneous province. Linked with ore deposits, and there are also some implications for oil and gas and indeed aquifers. And there are also planetary analogs, and we also recognize on Mars and Venus, etc. And we also see some Archean analogs, as I mentioned. I'm not going to go through everything, but I want to go through some thematic aspects that I think are particularly interesting and dramatic and important as we go forward. The first represents timing. There's been an enormous amount of new results in recent years showing the incredible shortness, the brevity of some of these events, where massive volumes of magma are in place in unbelievably short geological periods. First of all, with respect to the Deccan event, you see these very nice uranium lead diagrams, and you see the results and there's a theme here that I'll reiterate also, is that these events tie in very tightly with known extinction events. So with respect to the Cretaceous tertiary boundary and the demise of the dinosaurs, the precise dating shows that the main phase of eruptions initiated about 250,000 years prior to the extinction event, and that over 1 million cubic kilometers erupted in less than 1 million years, so in about 750,000 years. So that demonstrates that the Deccan event of India, the flood basalt event of India was associated with the end Cretaceous extinction event. Of course, it's also known that the Yucatan Peninsula meteorite impact was at about the same time. So in this particular case, it's a 1-2 punch. A meteorite impact and the flood basalt or lip event caused the end Cretaceous, the end of the dinosaurs. As we go back in time, okay, one of the other dramatic events at 200 million years ago is the Central Atlantic Magmatic Province known as CAMP. It's associated, it's found on North America, Africa, and South America in this reconstruction, and represents the event that just precedes the opening of the Atlantic Ocean at 200 million years. And you see there's also a radiating dike swarm on all blocks here, and a well-defined mantle plume center here at the center of activity. In terms of age, this shows the known extinction, the end Triassic, beginning Jurassic extinction boundary, and you see that these very precise dates from Blackburn et al. And is right straddling the extinction event and continuing a little bit younger. But notice the scale here. This is 500,000 years here. So this is incredibly tightly linked with the end Triassic extinction. Finally, dramatic results with respect to Russia's most dramatic large igneous province, the Siberian trap event at 250 million years. I'll have a diagram later, of course, to show the event, but you can see that the boundary as well, the extinction boundary, the Permo-Triassic extinction boundary is well defined here, and you see precise uranium-lead zircon ages just preceding, associated with and continuing afterward. But again, look at the scale here. This is just from here to here is 1 million years. This is really the smoking gun that the Permo-Triassic extinction was caused by the Siberian trap large igneous province. However, not all large igneous provinces are such incredibly short duration. There are others that seem to be multi-pulsed and extend for some 10, 20, or 30 million years. As an example, this is the Keweenaw Rift event of central North America between Canada and the US. And it represents a lip event that started to break up the continent here. And so it is multi-pulsed in the sense that there's an initial mantle plume event and a second pulse associated with the onset of rifting. It didn't succeed in opening up North America because at the same time on this side there was compression associated with an orogenic event, an ocean closure event. And so despite the attempt at opening a new ocean, it was prevented by prevailing plate boundary stresses. A little bit more about the link with extinction events. I showed the examples with respect to the Deccan event, the Central Atlantic Magmatic Province at the end of the Triassic, and the Permo-Triassic events as good here, here, and here, with the large igneous provinces associated. As well, many of the other times of major extinctions are associated, many of these peaks then, are associated with known large igneous provinces. Of all of these events, the one that doesn't yet have a lip event is the End-Ordovician event. However, I think we're on the track of that with respect to some units that at 440 or so that we see in the Verkhoyansk region, and some of the units that I know Andrei Izov is working on down in Mongolia, I think, that are represented of around 400, 440 million years. So I think we're on track with the potential to also include this one. But nevertheless, it seems that the extinction record through Earth's history is primarily linked to large igneous provinces. There's an aspect that I don't think I'm going to have a chance to discuss, which is to say that the full range of processes that link a large igneous province to extinctions is complicated and multivariate. It turns out that you can have large igneous provinces that cause global warming by pumping lots of CO2 into the atmosphere. It turns out you can also have large igneous provinces contribute to global cooling and ice house conditions, as the Sturgeon glaciation seems now linked to a large igneous province, where part of the story is that weathering of basalts is a huge drawdown for CO2. And so if you have your large igneous province mainly in a tropical area, the weathering will draw down CO2 dramatically and could put you into a glacial climate. So this is with respect to the seismic traffic, and you see a range of ways that it contributes to terrestrial mass extinctions and marine mass extinctions. And I won't go into all the details, but it's a complex story, but it is part of the way that we see large igneous provinces contributing to extinction events, but also in a broader way contributing to dramatic changes in atmospheric conditions and seawater composition as preserved in seawater in sedimentary record. I want to now go to another topic here, which is with respect to continental reconstructions and the role of large igneous provinces with respect to that. One of the sort of holy grails of our sciences is to sort out the reconstruction of continental blocks through time. We understand the supercontinent Pangea very well, and we have strong reasons to expect that there were prior supercontinents at about 1 billion, known as Rodinia, at about 1.7 billion years ago, known as Nuna or Columbia, and then in the late Archean, whether it was a single supercontinent or multiple large continental masses is not clear. And what's not clear is the exact configurations at any of these Precambrian supercontinent reconstructions. There are some robust attempts at reconstructions and some aspects of the Rodinia reconstruction as a result of a major IGCP project a few years ago, and some aspects of the Nuna-Columbia reconstruction and some aspects of the late Archean reconstructions are in fact well known, but in the main, these reconstructions have lots of uncertainties, and the individual placement of any particular block should be taken as speculative in most cases. There's a new IGC project 648, which is a global supercontinent reconstruction, global dynamics one, that is, I think, over the next few years going to yield some serious progress. And part of that progress is going to come from the more ardent use, more systematic use of the large igneous province story. If you look at the Pangea story, the Pangea breakup, the Gondwana portion here, is really dramatically linked to large igneous provinces, as I said. First of all, the Central Atlantic magnetic province here is linked to the breakoff and the opening of the Central Atlantic, the breakoff of North America. Each of these other stars represents mantle plume centers and associated large igneous provinces associated with the breakup of pieces of Gondwana. So the Paranapa large igneous province here at 130 million years is associated with the opening of the South Atlantic and the separation of South America and Africa. The Peru event at 180 in southern Africa and adjacent portion of Antarctica, associated with opening here. There's the Madagascar lip at 90 million years ago, the Deccan lip at 65 or so. And so each of these is associated with the opening of and breakup of Gondwana. So we expect that the exact same pattern works back through time. And so one of our goals in understanding large igneous provinces through time and finding the mantle plume centers is to try and use that technique to figure out the reconstructions back through time. This is the Superior Craton of Canada, Archean age crustal block. We now know that this block has been cut by major events, through time, each of which has an associated radiating dike swarm here, each of which has a mantle plume center at the edge of this crustal block. These two here the Mycene event and the Metatron event here are specifically conjugate to what we think is the Cola Corellia crustal blocks at the time with the same age of magnetism. And from this side, we recognize that there are two discrete plume centers here that are associated with this range of magnetism. We also have other centers here, 2100, 2080, and we think there's other crustal blocks here. On this side here, we're also experimenting with the idea that Zimbabwe was attached at this time in the Paleoproterozoic and maybe the Yilgarn craton of Australia, and so on. So we suspect that as we push this methodology back in time, find more and more radiating night storms, we'll have a fuller picture of how the blocks are to be reconstructed. So how do we do that? One of the things, the approaches that we use is what we call lip barcoding. If we've got several crustal blocks here, and we have known lip events, remembering that they are in many cases very short duration, if we've got a certain pattern on one block, another block, we can look for correlations. Here we see that craton A has many matches with craton B, D here. And so this is high likelihood that cratons A and D were near neighbors. On the other hand, craton A and B have no matches. There's no matches here. Craton A and B were not nearest neighbors. The other thing is we can use restoring radiating dike swarms. Here, in the example that I was showing before, we have radiating dike swarms that we continue into Cola Corellia, maybe Zimbabwe and Wyoming. And so that technique of the radiating dike swarms is useful for reconstruction. One of the key things then is being able to date goldrites. We've gotten very good at it these days. The mineral medelliite is particularly useful in that it is not inherited and does not survive metamorphosis. So if you get a medelliite age from a goldrite, it is the emplacement age. It is not inherited age. So we're very good at dating goldrites now, and using medelliite and paleomagnetic geochemistry are very important as a correlation tool to extend, paleomagnetism then obviously is a good tool for reconstructions once you have the age for a unit. We had a major industry-supported project over the last few years where we had $1.5 million from industry for systematically going around the world and dating dolerites. And we did a lot of that work in Siberia in particular. And as I'll show you, we were able to produce some new ages that recognize a whole bunch of major large igneous provinces, Precambrian, in Siberia that we didn't know about before. We produced about 220 uranium-lead ages, medelliite ages. Okay. And one of the sort of prizes of that then was we produced about 9 uranium-lead ages from southern Siberia, and that led us to a reconstruction of southern Siberia, Lake Baikal, here with northern Canada. These are the Arctic Islands in northern Canada. Southern Siberia, not northern Siberia. This is Alaska here, a piece of Alaska that presumably was in here as well. And we just had this published in Nature Geoscience. And what we found then was by looking at southern Siberia and northern Laurentian, and all the yellow boxes here indicate new events that we dated through uranium-lead medelliite dating. We find a whole bunch of matches throughout the time, from 700 million years all the way back to 1900, that demonstrate an attachment between southern Siberia and northern Laurentia for over 1 billion years in the Proterozoic. And some of the events then that get reconstructed into this are quite exciting. Dramatically, we have this huge event in northern Canada called the Franklin Large Igneous Province. And that is, it consists of a huge radiating swarm here. It covers about 2 million square kilometers in northern Canada, extends over. It has major mafic, ultramafic magnetism in the northern part here, and we interpret this to be the mantle plume center. On the Siberian side, we have this event we now call the Irkutsk event. Here's Lake Baikal, here's the Irkutsk here, and we have a portion of a radiating swarm, the intermediate section here, which presumably would have radiating dikes is not exposed. I do hope that, I'm very intrigued about the drone technology, which for aeromagnetic mapping, which you mentioned at the beginning here. I'm very curious about the availability already of aeromagnetic data that will allow us to see dike swarms and the potential for such stuff as more aeromagnetic data is collected. Canada has benefited from having near total aeromagnetic coverage in the 60s and 70s and 80s, and so it's been a huge boom for us being able to trace dike swarms, but also for basic geological mapping. Anyway, we interpret that the Mantle Plume Center for the Irkutsk event is also here, and so this provides a very tight constraint on this. There is interesting mafic, ultramafic magnetism associated with the Dvorin, the Upper Kingash, Tartai blocks. There are intrusions here that are economic nickel, copper, PG integers. So this whole event is interesting, and by combining it, we're combining the Siberian portion with the Irkutsk portion into a single event. And so the study from the Canadian side and the Russian side represents an opportunity for a more full understanding of what was originally a single event that would cover about 3 or 4 million square kilometers. Here's another event. We have a huge Mackenzie event in northern Canada that you saw in the other diagram. And we have a dike here in, major dike in, I think it's the Sharajagai block of southern Siberia there, that's about 10 million years younger. So it's our first sniff of the continuation of the Mackenzie event. Otherwise, I want to draw attention to this event here. Here we have a radiating swarm. Here, this is the Chara-Sinsk-Galui area here. So you have a radiating swarm here in the Chaya area, and in the Aldan and the Anabar Shield, precisely dated dikes, a radiating center here. We also have the same age in adjacent site in Laurentia. We also have a major event here, 400-kilometer long dikes, precisely dated 1870. Some dike here, the same age, and then we have a major province in slave Platon of the same age. I mentioned the talk yesterday by Ilya Prokopiev, talking about the Seligar carbonatite, which is approximately this area and is similar age to these dikes. This is a theme that I think is going to apply throughout. As we develop the framework of the large igneous provinces, we will be able to hang onto that frame all sorts of ore deposits that are linked to these events. And this, for instance, would be an example then of these carbonatites being linkable to this event. Look a little bit now specifically at the area of exploration. As we look through the record, we see an association between some of the largest lip events and major types of ore deposits. Nickel laterites in the Caribbean, associated with the 90-million-year-old Columbia Caribbean lip. Of course, the magnificent Norilsk nickel copper PGEs, associated with the Siberian trap lip. In Central Asia, there's the Morantau gold, which is of the same age as the Turin lip. It's a more complicated relationship in there. There's also major shear zones there, so it's not just, there's an age association with the lip, but there's also other controls that seem to be related to the Morantau. There is an age link and some genetic influence, presumably from the Turin lip. Siberian diamonds, many of them then seem to be associated with the 370-million-year-old Yakutsk-Galui lip. Sedex deposit in Western Canada, associated with this lip. Olympic Dam, this magnificent IOCG deposit in southern Australia, the Gulf Craton, is part of this major mafic ultramafic event. The Palabor carbonatite, which has major copper ores, is exactly the same age as the Bushveld large igneous province. Hammersley iron formations in part are associated with this Woongoor-Wingwooli lip of the southern Pilbara of Australia. This is another look at the lip family here. Flood basalts have a range of ore deposit types associated with plumbing systems and some ore deposit types associated silicic magnetism, associations carbonatites and kimberlites, Archean examples, oceanic plateaus. So there's a bit of a developing framework for what kind of ore deposits one might expect. effect. And we've developed distilling this into a sort of 5-part classification on how lips can be related. This is work I've been doing with Simon Jow, where one category is lips are the primary source of the commodities. So with respect to nickel, copper, PGE associated deposits, no rails, this would be this kind of deposit. And we find that most of the world's major nickel, copper, PGE deposits are linked to lips. The other thing is lips also provide energy to drive hydrothermal systems. This is an aspect we're trying to develop more. And as we'll see, it also can affect the maturity or over-maturity of hydrocarbons. Lips, particularly sills and dikes, can act as barriers to fluid flow and or as reactive zones, so as fluids are moving through, they either get blocked or they get precipitated out by the sill or the dike. And they can also, from a hydrocarbon perspective, they can also be a structural trap. And then weathering of lip rocks, laterites, and then in this category I'm also going to mention the oceanic anoxia events that are linked and which are the source rocks for hydrocarbons. This is with respect to then several large igneous provinces here. Here's the Siberian Trap event, the on-Craton portion, the portion of the West Siberian Basin, and here's the Norilsk area here. Here's the Mantle Plume Center here, depending on how you define the base of the radius form. Here. So this is proximal to the plume center. In the case of the Mackenzie event, the Muskox intrusion, famous in classic differentiation literature, the Muskox intrusion, that's part of this event, and it has some interesting mineralization that's near the plume center. Here's a major in northern Canada, the Circum-Superior large igneous province in 1880, associated with the Thompson nickel belt mineralization and the Raglan belt mineralization. And at least this portion is close to the plume center. Here in this camp event, the Freetown layered intrusion, major in terms of PGEs, is in the vicinity then of the plume center. So our story at this point, as we developed it, is that in many cases where you want to look for nickel associated nickel copper PGEs is proximal to the plume center. But there's also probably a link with a whole range of hydrothermal ore deposits, and this is an aspect that we're still trying to sort out. This is from a paper in Frank Ferraro, but other people this has also been reproduced in a number of other publications. You can see the nickel copper PGE of Talnac and Norilsk here, but you see all these other types, commodity types here that are distributed quite widely and there's also a paper by Borisenko, where you see all of these different kinds of ore deposits, including mercury and gold and antimony and copper and molybdenum, widely distributed and at age similar to and slightly younger than the Siberian Trap event, and in some way therefore likely being influenced by it. The details of that association are not well sorted out apart from the age correlation. You also, okay. So to jump to another aspect here is with respect to kimberlites. A few years back, it was recognized that in the Bastar Craton here, which is a portion of India with a deep lithospheric group, it has some kimberlites of age that are the same as the Deccan large igneous province. So in this particular case, one can envision a mantle plume that comes up, where the lithosphere is thinner here, you produce flood basalt magnetism. Where the lithosphere is thicker here, that portion of the plume ends up producing kimberlites. When one looks at South Africa here, very rich in kimberlites of a variety of ages. These are color-coded then in terms of their ages. And you can see an age-wise correlation with some of the plumes in the vicinity. Here's the Madagascar lip at this time, known from magnetism on Madagascar, which was reconstructed here at this time. And you can see a whole bunch of kimberlite groups that are tied in age-wise with the Madagascar plume. There's a whole bunch of plumes that are kimberlites tied in with the Paradox at 130 billion, and also apparently in the Congo Craton. a lot of kimberlites of the same age. So this mantle plume here, which was responsible for magnetism in South America and the Namibian portion here, or the Edeka portion of Africa here, and ocean opening up the breakup there, is also responsible for, seemingly for contributing to kimberlite magnetism over a wide area. With respect to Siberia, as we were seeing the other day, there's quite a large number of kimberlites that are associated with the, around 360 million years ago, that are associated with the Yakutsk Plume Center, the Yakutsk Beloui Lip here, which is shown here. This is the Plume Center here. You see major Charasinsk, Beloui Marco rift systems here, so a beautiful radiating rift system, beautiful pattern of radiating dike swarms with some complexity associated with the opening along this zone here, but overall a radiating pattern here of impressive swarm. And these associated kimberlites, which are out, where are they? I think they're out here, are diamondiferous and associated with this thing. These kimberlites here are slightly younger than the Siberian trap event, but are close to, are probably linked with the Siberian trap plume. Let's go on. However, some kimberlites clearly are not plume related, and there is an argument for plume where you have sort of a hotspot trap beneath continents. So while oceanic hotspots do not continue much into continental areas because they have a hard time continuing getting through continental crust, the overriding of a plume by a continental crust doesn't necessarily, does seem to allow the potential for some of that kimberlitic magnetism to actually traverse the continental crust. And so this example from the even Bruce Kiersgaard shows an age progression from northern Canada here down into the great medial hotspot track of a kimberlite track, and then becoming a normal hotspot track. This is another aspect that Dr. Pozo and others and a group from Oslo have been working on, dramatic stuff with respect to the role of hydrothermal vent complexes, interaction of this intrusive component, particularly sills, with sedimentary rocks, and the release of major amounts of volatiles from that as a major component of how large igneous provinces cause extinctions. So this is an exciting area in the Siberian trap in particular. There are hundreds of these things. The green triangles here, see, and then these circles here are all hydrothermal vent complexes, and these here are filled with magnetite. So potential, some of these are being mined. So this is a component of large igneous provinces we did not recognize them about 10, 15 years ago, and it seems to be a ubiquitous portion. This is just one aspect where there's sort of an indirect link. One of the things we're thinking about is, as you go back in time, it's hard to know when continental breakup is happening. But the large igneous provinces seem to, in their association with breakup, they also provide us a way to date timing of breakup. And so if you have breakup on one side of the planet, elsewhere you're going to have convergence. So the timing of breakup should represent the timing of increased convergence or transpression elsewhere, which has some implications for ore deposits. Orogenic ore deposits that may be correlated time-wise with timing of breakup on some other part of the planet. That's part of the reason we've had gold companies interested in our work, because of the potential of making that link. Oil and gas, so just three aspects. Oceanic plateaus as a cause of anoxia events that produce black shales and represent a source rock for oils. The thermal pulse from a large igneous province can cause maturation or overmaturation of the regional hydrocarbons. Dolomite sills as cap rocks for Here is, for instance, an oceanic plateau, the Caribbean large Igneous Province, leading to an anoxia event that could produce black shales and so on. There are a lot of anoxia events back through time here, and many of these then are linked in with oceanic plateaus, particularly the Selly here with Antamjava, and all of these that are around 90 million years ago with these large Igneous provinces. And just a little bit of thermal pulse can take you from immature to mature to over-mature in terms of hydrocarbon composition. For example, when you look at the camp event in Morocco here, or in Algeria, in this particular basin, you have a thermal spike that's recognized in the record there at 200 million years. That is exactly linked with the Central Atlantic Magmatic Province event. So in summary here, we were looking at, in terms of lips and resource exploration, a variety of ways that there are links. Primary source of the metals, heat to drive the engine, barriers to flow, reactive zones, surface processes, and indirect links. Just a couple other things I want to talk about. One of the themes, which is sort of a new area. We've been recognizing radiating dike swarms for a long time. This is the Mackenzie one. This is the Franklin one here that we saw before. This is another one here that we recognize in northern Canada. They are ubiquitous. We're finding them all over the world now and back through time. Here's the Central Atlantic Magmatic Province as well. There's a whole new class of radiating or swarms that we're just beginning to recognize. We call these giant circumferential swarms, giant circular swarms. Here, Lake Victoria, the East African Rift System, is a beautiful 180-degree circumferential system. This portion here will probably be revealed whenever the war stops in the area here and we can get proper aeromat. So 600 kilometers across. This one here would have a radius of about 300 or 400 kilometers. Here, the Siberian trap event, there's a circumferential swarm here in addition to the radius, circumferential swarm. Here in the high Arctic, this is 1,700 kilometers across. So we're talking about a circular swarm, not on the scale of an individual volcano, but something that is hundreds to over 1,000 kilometers across. These events are the same kind of thing that we see on Venus. This is where planetary comparisons help. On Venus here, you see rift systems here in red, volcanoes that are up to 500 kilometers across in green. These circular structures called corona. These circular structures called corona are characterized by these circular systems here. Here's the largest one, which is 2,600 kilometers across. We think that the circumferential swarms we're seeing on Earth are the terrestrial analog of these features that we see on, we recognize on Venus. So we have a planetary program. So just in terms of, we're just at the end here now, just to say that we have a mantle comes up, it partially melts, it produces some magmatic underplating at the base of the crust, it produces an array of intrusions within the crust, including dike swarms that extend out for maybe 2,000 kilometers in a radiating pattern, and maybe circumferential swarms that also extend quite far, then it feeds surface volcanoes. So that's the plumbing system. Some magnificent Siberian events here, the Siberian trap event here. The Yakutsk-Beluga event here at 370 associated with kimberlites. This 1750 million-year-old Siberian event, which in terms of overall extent covers extends over half the Siberian craton, and certainly a major event on par with the Siberian trap event. And it's precisely dated at 1755 plus or minus a few million years. So it's going to be one of these very, very short events. Okay. With respect to, this is the Canadian, this is the polar Karelia here. You see our two mantle plume centers here. There's all this layered intrusion of two different pulses here in northern Karelia and Kola. And which will probably should be linkable then with either this center or this center, depending on age. A major event in northern Siberia in the Anabar Shield here, that's all 1,500 million years ago, and potentially part of a reconstruction with the Congo craton and San Francisco cratons. And then all these events that we see shared between southern Siberia and northern Laurentia, which, yeah, I think this is the global water again. You see so many events linked with extinction events, linked with regional uplift, which I didn't detail, linked with rifting and breakup, linked with ore deposits, and a little bit of the planetary and arcane analogs. For more information, I have a book that just came out a year or so ago. The book's being translated into Russian, actually. And check out this website, igneousprovinces.org. We have a feature called Lip of the Month every month. So Lip of the Month, we've been doing this for 10 years. It covers terrestrial examples, flood basalts, Archean examples, Proterozoic examples, examples from Mars, Venus, the Moon, and Mercury, and so on. So Lip of the Month on igneousprovinces.org. And that's a final beautiful shot. Thank you all. Спасибо.
I think we have time for maybe a couple of questions, please.
What's, in your opinion, the best example of time-punctuated leap events, like reactivation of the same structures?
Reactive, sorry, what was it?
Reactivation of the same structures on the continents, time-punctuated.
Yeah, it's an interesting thing to think about. You know, the relationship between each separate event. It's oftentimes people say, we've got one continental block, we have one event after another. But if you take the global perspective, that's happening anyway. So in an individual block, if you have something that's 50, 60, 100 million years different, those are separate events. The blocks have moved, those are separate events. So, however, there does seem to be areas where you've had repeated activity. And part of that might be that if you think of plumes coming up randomly, if they come up underneath an area with a very thick lithospheric root, they're going to tend to come up and then slide along the root to shallower areas. So there may be, right, so they're not going to come up and do anything underneath the thick Siberian craton, they're going to slide off to the side of the Siberian craton. And so there's going to be a tendency then for these events to be channeled to areas of thinner lithosphere. So that would be some reason why you would have repeated activity in some areas.
Is the 90 MA Madagascar plume the same as 130 at Andeka and the same as 180 Karuk?
I think those are entirely different things, different plumes. And one thing about the 90 million, you have 90 million Madagascar, you have 90 million Colombia, Caribbean, you have a 90 million year pulse in high Arctic large igneous province. So you have at least 3 different nodes of 90 million, almost exactly the same age, in very different parts of the planet. So even those, I'm not sure what the relationship is. It may be something happening in the core at that time that puts an extra pulse into, a little quickening of the core and putting an extra pulse of thermal energy into, the core mantle boundary. But, yeah.
Please.
I would like to ask, still there are voices against you.
There are.
Activity.
Yes.
What's the name, the strongest?
Yeah, can I name the strongest of the...
Strongest against.
Oh, well, there's certain people like Jill Bolger and the late Don Anderson and others who certainly argued that mantle plumes, or Warren Hamilton, various people who've argued that mantle plumes are not the cause for these large volume, short duration events. I think as more and more data is accumulating, I think it's harder for such a position to be maintained. As one increases seismic tomography evidence, we're seeing increasing evidence for the actual conduits of mantle plumes. I think our story related to radiating dike swarms is particularly dramatic. we're finding more and more of these giant systems which radiate away, and now we're also developing these circular structures. You have point sources of this magnetism. That seems best explained by Bloom. And then there's arguments related to, the impact. Impact is also hard to sustain. When we look on Venus, for instance, where we can see impacts very clearly, and magnetic centers very clearly, and they are entirely different looking. So, yeah.
Please, just the last question. We are reaching out of time.
First, thank you very much for very interesting presentation. So, in particular, you mentioned some relation between hydrocarbon production and relation with some chemicals. My question: do you think that this enormous Russian Gulf hydrocarbon accumulation might be related with some major
I'm at the learning stage. I'm very interested in that question of various reservoirs around and what the controls are. I don't know very much about it yet, so I'm really trying to learn to see whether there are other examples where what are the specific influences from magnetism. So I don't have an informed opinion on that yet.
if you go completely applicable to the case of Eastern Siberia, for example, I'm fascinated with these days. But this enigma, how this enormous quantity of hydrocarbon produced in this restricted area.
No, I want to.
Do you think this is some, the major igneous event behind these?
Well, it depends what the ages are. We now have a good timing of events now. We have a much better understanding of timing. So we now have the tool from the magnetic side to compare with the hydrocarbon side and the understanding of, when the hydrocarbons form, when they
Now
get.
this is Cretaceous. Yeah. But it might migrate in the Cambrian.
Oh, really? Okay. Well, that's exciting. Certainly are Precambrian events that would be potentially relevant, right? So there is the timing of formation of the hydrocarbons, the timing and the causes of migration, the timing of, so there's, you're somebody who I would like to chat more with about this, because I want to explore this area more.
Thank you, Richard. I can feel that there are many questions, but let us leave it for a couple of breaks. Richard, thank you one more time.